Q7141. What can a pilot expect when landing at an airport located in the mountains? A. Higher true airspeed and longer landing distance. B. Higher indicated airspeed and shorter landing distance. C. Lower true airspeed and longer landing distance. The correct answer is A. When landing at an airport located in the mountains, a pilot can expect higher true airspeed and longer landing distance. Here's the detailed reasoning behind this. 1. Higher true airspeed. In mountainous areas, the altitude is higher, which results in lower air density. With lower air density, the true airspeed, TAS, increases for a given indicated airspeed, IS. This means that the aircraft will be moving through the air at a higher speed relative to the surrounding air molecules. 2. Longer landing distance. Due to the higher true airspeed, the ground speed of the aircraft will also be higher during landing. Since the landing distance is measured in relation to the ground speed, the higher ground speed will result in a longer landing distance. Therefore, when landing at an airport located in the mountains, a pilot can expect a higher true airspeed and longer landing distance. 6809. What is the significance of the blue radial line on the airspeed indicator of a light multi-engine airplane, and when is it to be used? It indicates the A. Minimum speed at which the airplane is controllable when the critical engine is suddenly made inoperative and should be used at all altitudes when an engine is inoperative. B. Speed which will provide the maximum altitude gain in a given time when one engine is inoperative and should be used for climb and final approach during engine-out operations. C. Speed which will provide the greatest height for a given distance of forward travel when one engine is inoperative and should be used for all climbs during engine-out operations. The correct answer is B. The blue radial line on the airspeed indicator of a light multi-engine airplane is significant for engine-out operations. It represents the speed that will provide the maximum altitude gain in a given time when one engine is inoperative. The correct use of the blue radial line is during climb and final approach in engine-out situations. When an engine fails, the airplane's performance is affected and it may not be able to maintain its normal climb rate. By referencing the blue radial line, the pilot can adjust the airspeed to maximize the altitude gain within a specific time frame. Choosing the airspeed indicated by the blue radial line allows the aircraft to optimize its climb performance during engine-out operations. This speed ensures that the aircraft maintains the best angle of climb, resulting in the greatest altitude gain for a given time period. It allows the pilot to efficiently manage the climb during critical phases, such as departure, obstacle clearance, and final approach. The blue radial line indicates the speed that provides the maximum altitude gain in a given time during engine-out operations and should be used for climb and final approach. 6807. In a twin-engine airplane, the single-engine service ceiling is the maximum density altitude at which VYSE will produce. A. 50 feet per minute rate of climb. B. 100 feet per minute rate of climb. C. 500 feet per minute rate of climb. The correct answer is A. In a twin-engine airplane, the single-engine service ceiling is the maximum density altitude at which the best rate of climb on a single engine, VYSE, will produce a rate of climb of 50 feet per minute. When an engine fails in a twin-engine airplane, the remaining engine must compensate for the loss of power. VYSE is the airspeed that provides the best rate of climb under this condition. It is specifically designed to optimize the climb performance on a single engine. The single-engine service ceiling is the maximum density altitude at which the aircraft can maintain a positive rate of climb of 50 feet per minute using VYSE. This altitude represents the limit of the aircraft's capability to climb effectively with only one engine operating. Selecting an airspeed other than VYSE may result in a lower rate of climb or even a descent in the event of an engine failure. Therefore, it is crucial for the pilot to operate the aircraft at VYSE during engine-out situations to achieve the best climb performance and maintain a positive rate of climb. The single-engine service ceiling is the maximum density altitude at which VYSE will produce a 50 feet per minute rate of climb. 6808. When one engine fails on a twin-engine airplane, the resulting performance loss A. May reduce the rate of climb by 80% or more. B. Reduces cruise indicated airspeed by 50% or more. C. Is approximately 50% since 50% of the normally available thrust is lost. The correct answer is A. When one engine fails on a twin-engine airplane, the resulting performance loss may reduce the rate of climb by 80% or more. In a twin-engine airplane, both engines contribute to the total thrust and performance of the aircraft. When one engine fails, the remaining engine must compensate for the loss of power. However, the performance of a single engine is typically not equal to half the performance of both engines combined. The loss of an engine significantly reduces the available thrust and power, leading to a substantial decrease in the aircraft's performance. The specific amount of performance loss will vary depending on the aircraft model, configuration, and operating conditions. However, it is not uncommon for the rate of climb to be reduced by 80% or more when operating on a single engine. This reduction in the rate of climb is primarily due to the decreased thrust available for climbing. With only one engine providing power, the aircraft's ability to climb efficiently is severely limited. The loss of an engine also affects other aspects of performance, such as cruise speed and maximum altitude capability, but the rate of climb is particularly impacted. When one engine fails on a twin-engine airplane, the resulting performance loss may reduce the rate of climb by 80% or more. 6810. When operating a light multi-engine airplane at VMC, the pilot should expect performance to be sufficient to maintain A. Heading. B. Heading and altitude. C. Heading, altitude, and be able to climb at 50 feet per minute. The correct answer is A. When operating a light multi-engine airplane at VMC, velocity minimum control, the pilot should expect performance to be sufficient to maintain heading is the minimum airspeed at which the airplane remains controllable with the critical engines suddenly made inoperative and the remaining engines at takeoff power. It represents the minimum speed required to maintain control during an engine failure scenario. At VMC, the pilot should be able to maintain heading using the available control inputs and available engine power. It is important to note that VMC does not guarantee the ability to maintain altitude or climb at a specific rate. The primary concern is maintaining control and heading. If an engine fails during flight and the airplane is operated at or near VMC, the pilot's main focus should be on maintaining directional control and preventing a loss of control or yawing tendencies. It may be challenging to maintain altitude or climb at a specific rate due to the reduced available thrust with an engine failure. Hence, operating a light multi-engine airplane at VMC, the pilot should expect performance to be sufficient to maintain heading.